remember when I introduced myself, I said I'm interested in the sort of creative aspects of automated reasoning. So in particular, this talk will be about the generation and suggestions of conjectures that might be interesting in some theorem-proving context. I'm going to talk about some rather old work and some quite new work and some work that's very, very half-baked, if that. But let me start with some history. So the idea of getting computers to automatically generate or discover mathematical conjectures is as old as AI itself. Already back in the 1950s, Newell and Simon very confidently predicted that within 10 years, a digital computer will discover and prove an important new mathematical theorem. This did not happen.
But somebody did get a physics Nobel in '63 based on computers.
Yes, and Simon won it in economics in '78 and so on, and they got a Turing Award in 1975. So even making very bold claims is, of course, not ridiculous. Even if you're wrong, there might be good things coming out of it, of course. But maybe the time is right now. So nowadays we have large language models, and they can capture some mathematical intuition, perhaps, in a way that symbolic systems couldn't. So this quote is from Terence Tao last year, where he predicts that, say, a 2026 level AI will be a trustworthy co-author in mathematical research. So we got 2 years, so yeah, what do we think? Maybe we're in a bit of a hurry then?
At the end of 2000.
At the end of 2000, we may or may not happen, we'll see.
Or he's just plain wrong.
Or he might be wrong, but you know, lots of good people are wrong, so we shouldn't blame them for being wrong. But anyway, I think it's there's a lot of course interest now, and there was a very nice article interview with said Terry Tao in the Scientific American, where he was speculating. This is from this year, so maybe it's a little bit more nuanced, where he's speculating how proof checkers and AI programs will change mathematics, what we've been talking about here this week. And how, for instance, mentioning the famous liquid tensor project in Lean, and how this allows for larger collaborations between larger groups of people, where results are checked by the proof assistant. So it's essentially allowing a very different way of working for mathematicians in larger teams. However, this of course relies on libraries of basic mathematics being already formalized or built up. And this, of course, takes time, and that's why we're here talking about autoformalisation. What can AI do to support this, to make it more quicker, to develop new theories, especially in this age of powerful generative neural model. So one of the things that he said in this interview was that he imagines that in the future, big theorems are proved by a combination of maybe 20 people and a bunch of AI, each proving little things. And over time, they will get connected, and you can create some wonderful things. So we talked about how we identify ourselves. I think I identify myself as an AI person. So I'm, of course, interested in building these little bits of AI that will do little things that might come together as a useful whole. Okay, so I'm going to talk about something called theory exploration. Sometimes it's called automated conjecturing. It's the same thing, which might be part of this puzzle of facilitating some formalizations by helping, given a new theory development, for instance, helping you generate some of the basic lemmas automatically, so you can focus on the more interesting stuff as a human mathematician. So basically the general idea, as I said, is that we want to assist invention. And of course, you could do this in a naive way. You could just enumerate stuff, but that's not very good because you will get an awful lot of stuff that you already know or that is not interesting. We can discuss what we mean by interesting later on if you want. I'm interested in interestingness. And also you want things that are non-trivial. I think all these things really, they are contextual. So it depends on what you already know, what your system already knows, in which theory you are, and so on. A bit of history again. So theory exploration is not something new. That's been going on, and it's been things happening since the 50s. So you have systems like AM by Doug Lennart in the 70s, which had a very complicated setup with a load of complicated heuristics, something like 250 rules. So it was a bit controversial. He claimed that this system rediscovered, for instance, Goldbach's conjecture. But it was a bit controversial. Maybe among these 250 rules, there was too much kind of guiding it to exactly where they knew they wanted to go. So this was controversial. There's also a system called graffiti from the 80s, which was applied in graph theory and chemistry. So there was a lot of inequalities that they wanted to generate there. There's this called HR and HRL, which was also doing model finding, and conjecturing was done via a set of production rules. So you still have very rule-based systems. Also the MathSaid system that came out of Edinburgh, where I also did my PhD with Alan Bundy. So I worked on some systems, first one called Isacosi, which was conjecturing for Isabel, and then later on a system called QuickSpec, which is developed at Chalmers, where I am now. I think I should say that maybe, so my entry point was that I was working on theorem provers for automating proofs by mathematical induction. And one of the things that you have there is that it's undecidable because you might always need an extra lemma. You might need to go and prove that lemma by induction and so on. So I was very interested in looking at proofs when they failed. Could we come up with a lemma? Turned out that was really hard to implement. So at some point I got fed up and said, okay, well, why don't we just synthesize a bunch of conjectures that seem relevant, and then we try them out and we don't have to do all this hierarchical unification and so on. So that's what we did. So instead of going top down from a proof that we're trying to prove and try and generate lemmas, we said, okay, well, if we're in this theory, what could be some interesting lemmas? We generate those, and well, at least that kind of works for many of the benchmarks that we have lying around. So this has been integrated with various automated provers for induction, both in Isabel and most recently last week at HCAR. Solveig and Egnarsdottir, who's a PhD student, presented this paper here that combined vampire. So vampire is an automated first-order prover which can now do induction, and we experimented with adding also lemmas to vampire, and it worked very well.
Moa,
Yeah.
was it integrated in this year's task because vampire is often here to jump from 370 to 470?
So we had nothing to do with that.
All right.
So yeah, no, that was not our doing. So yes, unfortunately. Anyway, so theory exploration. Coming back to what does that have to do with autoformalisation? Well, I think there are two things. So hopefully we can maybe help generating some of the boilerplate boring lemmas that you need, or that are maybe not interesting for a human, but they're very useful to have for automation in a theorem prover. So for instance, something like Sledgehammer, these ATP tools that you have in Isabel and soon in Lina here, that could be very beneficial for them because they have a few more things to use. Perhaps it might also be useful for assisting translations between formalism. Maybe you need some lemmas that are slightly different because one prover reasons in a different way and might need different things. So these are my speculations on where it might be useful in this context. So first of all, I will do a little bit of a demonstration of one of these conjecture generation systems, namely QuickSpec 2. QuickSpec is written in Haskell, so it started off as a system for taking Haskell programs and generating specifications for them, and in particular then equations describing what some function does, essentially. So this is kind of the properties that you write down. I don't know if anyone here is familiar with property-based testing, but the style of properties that you would write down for a functional program when you do property-based testing. So I'm going to do a little demo here about something called the octonions, which I didn't know so much about because I'm not a mathematician, but it was in Ursula's slide somewhere near the top, together with its friends, the real, the complex numbers, and the quaternions. What me and my colleague Nick did was to say, okay, well, we can at least define these in a Haskell program, formalize them as a Haskell program if you want, and then we can run our tool, QuickSpec, on them. And let me see if I can get this video to run. No? Why not?
It's running.
Oh, is it?
Yeah.
Oh, great. Sorry, I didn't see it on my screen. Yes, that was QuickSpec running in real time, so it doesn't take very long. You feed it the program, it comes back with 14 laws. So you can stare at them for a little bit if you want, and convince yourself that they are somehow interesting. So one thing you should notice is equation 13, which is a consequence of the fact that multiplication on these octonions is non-associative. So then equation 13 apparently has a name. If we go to the textbook, it's called the Mufang identity. So that shows that these octonions make up something called a Mufang loop. This was used to us, not you mathematicians, but us computer scientists. And in fact, 12 of these 14 properties that QuickSpec discovers have names if we go and look them up in a textbook. Of course, it would be very nice if we had a language model, maybe, that could go and say, well, by the way, that one is the Mufang identity, and this one is the left alternative loop property, and the automorphic inverse property, as they're called.
So, Moa, can you say again what the input to the...
So the input here is a Haskell program. Basically is defining what octonions are, and also defining the multiplication function and the inverse function. So it's nothing strange. It just happens to be formalized as a Haskell program. Yeah.
And for the reals you use floats, or
Sorry?
for the reals you use floats?
I can show you the formalization later on. I don't remember, but I think we used the built-in library definition in Haskell, essentially. So probably some floats. Okay, so QuickSpec can take either a Haskell program as input or some input in a format called TIP. So TIP is very similar to SMTlib for those of you who use SMT solvers.
These are laws that it guesses.
Yes. So these are laws.
So it's like law number 4 is just false, right? There's an exception with x is 0.
Yes. Okay. If you say so.
It's going to be a fight.
Yeah. So yes, the last bullet point here. We haven't proved anything yet. I've just conjectured it. And the way QuickSpec works is that it generates these terms, the left-hand sides and the right-hand sides. It's going to evaluate them on random test cases. So you see your x's and your y's, they're going to get replaced by random concrete values, and you evaluate them. And then you build up equivalence classes of terms that happen to, in all test cases that we've done, which is a few hundred up to 1,000. So in case there might be something slipping through here, the odd non-true equation.
You don't have zeros, right?
Sorry?
You don't have zeros. Do you?
No, actually, yes, I only had one there, but so that might be.
Yeah, well,
you
your
have
underlying model.
I'm gonna have to go back and look at the program. This program is probably some example I've been running for 10 years, so I don't remember exactly. we can look at it later. It's entirely possible that we've made some mistake as well. We're not mathematicians. We're stupid computer scientists.
But I think this is fine. Like this is like just a multiplicative.
Well, 5 isn't going to be true for x equals 0. 4 might be okay.
4 might be okay, 5 is, yeah.
And 10 also.
It's great you're arguing now
So,
about
so these
my
14,
conjectures.
you could also have asked for 30 or something like this?
Sorry?
This 14 is part of your script. I mean, you could also ask for 100 or something like that?
Yeah, so in this case I get 14 because I've said that I want to go up to a maximum size of 7 symbols on
Okay.
either side. So that's why. So this is part of how Pixpec works. It starts by generating small things, start building up these equivalence classes. And this is what makes it fast. This is why it ran in like a second or so, because this way we don't have to explore things that are subsumed by any of the equations that we know. So there's a lot of machinery going on here. There's a really good equational theorem prover actually to make sure that we don't generate any things that are just subsumed by any of these other equations. You get the most general versions. But anyway, as we noticed, we have only tested these, we haven't proved them, and there are various opinions about which of my properties are true. So, of course, a second step would be to give this to a theorem prover, or calling this, for instance, from a proof assistant. So we've done a sort of embedding of this into Isabel. It's a system called Hipster that I wasn't planning to demo in this talk, but there you can get the conjectures and then run them through a loop which tries to prove them with some tactics in Isabel that you have specified yourself. So that could be, for instance, sledgehammer or some custom induction tactic or whatever you want. And you could also then specify a tactic for, I said I want these to be interesting and new, so you can specify a tactic, a simple tactic, like simplification, for instance, and if something can be proved by simplification, then you can say, okay, maybe I don't show this to the user because it was probably known already. So then you can do a little bit more customization and filtering on these. Okay? Any more questions?
And you have just syntactic rules that transform this.
Yes, so this is a purely symbolic system with a lot of clever implementational tricks, I would say. But it's pretty good, it's pretty fast, as long as you don't want to go up to terms that are bigger than about this, then it's fast. At some point, yes, you are going to hit exponential growth and it will slow down. But for fairly small properties, it's really fast and quick.
Wait, so like these are all like named properties.
Yeah.
If you start going to 5 terms, you're probably going to start finding things that don't have names. Are those new theorems?
They might be, but I don't know if a mathematician would like them or find them interesting. So, yeah. They are conjectures also, so you can have them and you can prove them yourself or something. Okay, but this is the general idea of theory exploration. Let me also say that there are, of course, data-driven and neural methods for doing this kind of task. So, for instance, Joseph, of course, have worked on this already in 2020, where they generated conjectures in MESAR with the GPT-2 model. And there's also been some work for whole light. But the problem there is that, of course, you get a lot of stuff, but quite not very much is new or interesting. You get a lot of repetition and false things. So you're more, in the neural models, you really do need some sort of filter there. So QuickSpec at least generates a fairly small set already from the get-go. Some other there are also some data-driven non-neural models that I've been involved in, where we, rather than generating just everything, we try to restrict the search space by finding some patterns of common lemmas or similar things, lemma schemas I call them, which we then instantiate symbolically. In these lemma schemas, they might either come from, so in the RUBSpec system, which is the most recent one, they simply came from the user, and we're currently working on extending that to learning such patterns. And this reduces the search space, of course, and allows you to do things that are maybe not just equation and not so size limited. So it gives you a bit more flexibility. But we will come back to these things, because, of course, as Joseph said, Moa is going to talk about LLMs, so then I have to talk about LLMs. So this feels very 2023. Yes.
Can I ask a question before that?
Yes.
So do any of those take existing knowledge in terms of theorems that are around and so on into account?
So QuickSpec doesn't do that in the generation. Hipster, which is this Isabelle embedding, does do that on the proof side.
Okay, but not during...
Not during generation. So yeah, again, this is like, yeah, it would be nice to have feature, but yes, please give me money so I can pay someone to do it, which hasn't happened, so yes. Anyway, this is very 2023. You have to try everything with ChatGPT last year. So of course, me and Nick, who's the head developer of QuickSpec, we said, okay, yes, we have to see if we ever have to continue developing our tools. Maybe ChatGPT can now generate lemmas 0 shot. So let's, oh, this looks funny. So let's explore something. Well, of course, we know that ChatGPT is trained on the internet, including all our benchmarks. It was very good at doing our benchmarks, and it's even kind of copied them. So yeah, okay, we have to do something new. So we decided to go for a library, a Haskell library, which we ported into Isabelle Hall, which is about drawing. So this benchmark wasn't in Isabelle as far as we could tell, but it is, of course, exists in Haskell on the internet. So it's a bit exotic, so that's why we picked it. Here's loads of bunnies. Anyway, so this library is about manipulating pictures. So it consists of various combinators for building and combining drawings, such as placing them on top of each other or beside each other, with some interesting properties. So for instance, as you notice down there, the bunnies get squished because it keeps the bounding box. As it does this, you get some interesting properties of these functions. So, for instance, these are not the same. So, if you put the bunnies beside each other, you can't re-bracket it, because then different bunnies get squished. Basically. Right. So, poor bunnies. Let's see. So this is then, you don't need to read this very closely, but this is the formalization in Isabelle of this drawing library and all the functions of flipping and beside and above and so on. And we basically dumped all of this. We didn't do any fancy prompting. We dumped all this into Isabelle and then said generate lemmas in Isabelle format about the functions blank, over, beside, rotate, flip, and rotate 45. So let's see what happens. Remember, it's not associative. We squish bunnies. So here is the output that it produced. So this is one sample run. They vary a bit. Let's see. So let's first look. finds out that blank, if you put some blank picture over, or a picture over a blank picture, yeah, you get the same picture back, so that's fine, it's an identity element, but so that's fine, but it also thinks that if I put a blank picture beside another picture, I get the same picture back, which is not the case, because remember we squished them. So these are wrong, but it seems to like this pattern, so it applies it to all the functions that it has. Next, it likes associativity as well. So unfortunately, only the over function is associative, and the other ones, the beside and above, are not. But it likes that pattern. Next, commutativity, another pattern that it likes. Over is commutative, the other ones are not. And then we get some other lemmas. It thinks that if I rotate something twice, you get it back, but that's not the case. However, if you rotate, so this rotates 90 degrees, so it gets upside down, whereas this one is okay because it figures that here it seems to realize that rotate does it 90 degrees and that there it doesn't. So this is a language model. This is perfectly fine. It might hold contrary beliefs.
So how is this different than well-typed term enumeration?
So this is just completely done by language modeling. So basically what we get from a language model is what are some likely conjectures
okay, so these
about
are
this
linguistically likely
Yes.
things. That
Yes.
makes sense. Okay.
Yes, exactly. So it's pretty. It gets this about syntax right, which is kind of nice though. So how did it do here? Many of the conjectures were false, as you saw, but I mean that's fine. It's not a huge problem. We always have the theorem prover and the counterexample checker there as a safety net to take care of that. And in fact, we could prove the ones that are true here. They can quite easily be proved by something like auto or sledgehammer. So that's nice. And we can run the counterexample checker also get counterexamples of the ones that weren't true. One thing that it seems that this language model have internalized are some templates. So I mentioned templates before, that very often there are common patterns. We know that from algebra. We have our algebraic laws. So it likes to speculate that it's an identity element, binary functions, associative and commutative, and unary functions are their own identity. And sometimes binary functions distribute over one another. It varies, but sometimes it guesses that, yes.
Did the ChatGPT have access to the bunny value?
No, the bunnies are there for illustration.
Well, because I was wondering if you gave it a bunny, would it think the bunny is a unit of over and so on?
Maybe. Now I just had blank, I didn't have the bunny. But that would have been fun. Or I mean, we did play around with renaming functions to crazy things, and at some point it just said, no, you're doing something stupid. This can't be a real mathematical theory.
And it might generalize from the fact that this exists in Simon Thompson's book with horses instead of bunnies.
Yeah. Right. Yes, it also very consistently misses some lemmas that we would find if we were in quick-spec on this. For instance, that if we put one bunny on top of another bunny, it's one bunny. And some sort of more specialized lemmas, which is if you do some 2x2 grid layout and you put things in there, you can do that in different ways and get the same. And of course, it doesn't run on my old laptop, which QuickSpec does. So as someone was asking about energy and green images yesterday. Okay. I should show you also this. So this is an alternative run. So again, this is language model is probabilistic, so I might get slightly different results if I run it a second time. So this happens to be a particularly lucky run where we get these number 6 the rotations. It gets the number of rotations right, so you need to do 4. And it also managed to get the number of 45-degree rotations correct, as illustrated at the bottom. So there's some knowledge about rotations in ChatGPT. However, it does also miss that if you rotate 45 twice, you get rotate D, which it doesn't speculate here. So it's not complete. I should also say that this very, very long thing would not be generated by QuickSpec, just because when I run it normally, yes, I could if I gave it more compute, but typically we don't run it up to such long terms because the search space gets too big. Okay, yes, I already said this, so QuickSpec has a size limit. You can customize it. I could have given QuickSpec more compute and it would have come up with this. Probably would also have generated a lot of other very big things and it would have been a bit slow, so that's where we start getting to. Now I have 5 minutes, but that's good. I should also mention that the nice things with LLMs, though, is that they can use information from function names. So rotate sometimes at least gets rotated the correct number of times, and sometimes it suggested some extra auxiliary functions that would be nice to include that didn't exist. It hallucinated them, but they might have been nice to have. As we mentioned in one of the earlier talks, buggy definitions. So if I have a bug in my definition, QuickSpec will miss a property or generate some weird property, whereas the LLM might very often it doesn't read the implementation too closely and it comes up with the correct property anyway. So for instance, we had some bug in one of the rotate functions that we hadn't spotted, but we got the right properties by the LLM anyway, so it's not fussy about definitions, it guesses what we want. Okay, I have a few minutes left, so let me just say, I'm finally getting to the neuro-symbolic side, so there is some ongoing work now. I wouldn't know if it's even half-baked, but as I mentioned already before, we made this observation that there are statements in proof libraries that share some structure, so your common algebraic laws, for instance, but also some other ones. So Sulren did some experiments on the Isabelle AFP back 2 years ago, and she noticed that there is a small number of, so these are templates, the kind of shapes, you're with me, and there are a fairly small number of those that covers quite a lot of the, I think these were equations in particular from the AFP. So there's something like 22,700 equational lemmas, which are captured by 6,500 templates, but more than 50% of these lemmas can be described by a few hundred, 200 or so templates. So maybe we don't want the fully neural generation, but maybe we can train a neural model to give a new formalization that we're starting, suggest some templates, and then use some template-based generation to fill in these and come up with conjectures. It's not clear whether a fully symbolic, a neuro-symbolic, or a fully neural system will generate the best candidates. So that remains to be seen, but this is what we're working on currently. So should I just stop and take questions? I don't need to say that much about this slide if you don't want to, if I'm running out of time.
Well, let's leave a bit more time for questions.
Yes.